Welcome to lesson 35, Dielectrics. Here's the plan for today. A dielectric lets you store more charge without changing the capacitor itself. And the way it does this is by pulling charges closer together so more can fit. Here's the mechanism. You slide an insulating sheet between the plates. The electric field grabs hold of the molecules in that sheet and aligns them, polarizes them, so their negative end points towards the positive plate and their positive end points towards the negative plate. And that alignment partially cancels the field between the plates. A weaker field means less pushback against adding more charge, so the plates can hold more. The dielectric effectively pulls electrons onto the negative side and pushes them off the positive side, and the capacitor holds more charge at the same voltage. So how much better is it? We need a number, and that number is the relative permittivity given by epsilon r. And notice the pattern here because it recurs throughout physics. Whenever we want to handle a specific material, we bolt on a constant that makes things relative. It's exactly like resistivity. Relative permittivity is exactly that. It's the ratio of the charge held with the dielectric to the charge held without it. And since Q equals CV, at constant voltage, that's also just the ratio of the capacitances. Some examples of relative permittivities are polythene, which is 2.3, mica is 7, and surprisingly, water is 81. But when you think about the positive and negative atoms in the water molecule, it does make sense. Which gives us the full capacitance equation. C equals A epsilon R epsilon naught over D. Bigger plates give more capacitance, a smaller gap gives more capacitance, and a good dielectric multiplies it up. There are three ways a material can polarize, and it's cleanest to think of them by size, from largest to smallest. Molecular polarization is the largest scale. Water is a great example. It's a polar molecule, with a slightly negative oxygen end and a slightly positive hydrogen ends, thanks to its covalent bonds. Put it in a field and the whole molecule physically rotates to line up. That's why water has such a huge relative permittivity. The step smaller is ionic polarization. In something like sodium chloride, the individual positive and negative ions shift and align. Same effect, but on a slightly smaller scale. An electronic polarization is smallest of all. The electron cloud around each individual atom gets pulled to one side, leaving the nucleus slightly exposed on the other. Even a single atom can polarize a little, but this is the smallest mechanism. And here's an idea worth carrying forward, because it's about to become important. In every one of these cases, the material responds in a way that opposes the change being imposed on it. The system resists. Make sure to keep that in mind because it comes up in a few lessons' time. One final consideration with polarization mechanisms. What if we make the field alternating rather than steady? Then those poles have to flip back and forth to keep up with it, and that means inertia matters. A big, bulky water molecule has lots of inertia, so it's slow to turn around. Ions are smaller and quicker, and electron clouds are so light they can zip back and forth almost instantly. So as you crank up the frequency, the sluggish mechanisms drop out one by one. First the big molecules can't keep up, then the ions, and only until the electrons are still responding. And that gives you the permittivity frequency graph, falling away in steps as each mechanism is left behind. That's the end of the video, and the end of the topic on capacitors. Next time we start magnetism. Thanks for watching and check out my tutoring page below.